Okay, good morning. We start our session. The first speaker is Antonio Garufi. You're welcome.
Thank you. Thank you. Good morning. What? Yeah. This one? Yeah. Good morning, everybody. So for those who don't know me, I'm a disc imager. So some of the images you have seen and you will see are probably by me and collaborators. Today, in particular, I've been asked to talk about shadows, which is one of the most interesting features that we have in these images here. And this is just a quick collection of those discs that actually show these images. So I sometimes start in a provocative way. As a disc imager, I like to say that these are still the best images that we have of discs. Unfortunately, they are not real, of course, but basically the ingredients that we need to make a nice image are here. So we need a very good angular resolution, and in particular we need the capability to really resolve the inner disk regions, which is tough, especially in the near infrared. So this is a diagram that basically tells you how good is your image in terms of angular resolution and inner working angle, which is basically your capability to really go inside. And you can see that this was not obvious in the past. Even with the Hubble Space Telescope, the resolution was naturally very good as we were working in the visible, but we couldn't really access the inner regions because of the presence of a coronagraph or because of just the PSF was just not very well corrected for. So if you really want to go to the inner disk, which is basically, say, inside the Jupiter location or even more, we were, of course, very, very far away. Today, we are a little bit closer. Not quite there yet, but we are definitely closer with our VLT or Keck, Magellan and so on, all the 8 meters telescope. We are really at the edge of the Jupiter orbit, let's say, and ALMA is doing even better than this. So both in inner working angle and angular resolution, we improved a lot, but we're not quite there yet. So indeed, the inner disk is not yet mapped, so what is actually tackled in this conference is somehow a little bit far away from my topic, but we are developing some indirect methods to actually map the inner disk from our images. And one of these is, of course, the presence of shadows. So just a little bit of background on what is actually high contrast near infrared imaging. Unlike ALMA, you have to consider that it's not a matter of sensitivity. The problem is that basically any object is pretty bright in the near infrared, in the visible, so it's a matter of contrast. The problem is how much a certain object is bright compared to another. So a star disk contrast, envelope to disk contrast, star to planet contrast, and so on, depending on our purpose, but we always have another object which is basically impeding us to resolve what we want to do. So in particular, if you want to resolve a disk, the stellar flux is, of course, your worst enemy. So we have developed a number of differential techniques in order to remove what is actually your enemy. And today I will just mention the polarimetric differential imaging because this is where much of our focus is in the last years. So what is the basic idea? It's basically this sentence here. The stellar light is to a large extent unpolarized, say, for our purpose. The scattered light from the disk is to a large extent polarized. So that means that if we have a polarimeter and we observe the star simultaneously with two orthogonal direction of polarization, and then we can combine with some trick and some algebra, in the end we can basically obtain an image which is the tangentially polarized component of the light. So this is basically giving you everything that is scattered with respect to the central star. So everything is going from the star and then it's reflected here in the sun. So most of the scattered light from the disk. And then the stellar light is to some extent gone. But we have to consider that when we make these maps, the results of this max is actually given by a number of factors, which is basically a disk geometry, depending on the inclination and so on, depending on the angle that the photons is scattered by, depending on dust properties, so a grain would be more or less prone to actually scatter photons, and more importantly for this talk here, the illumination pattern. Of course, if you have 0 photons reaching the disk phase, you will have 0 photons that will be scattered. So you need photons to actually reach the disk phase in order to have scattered light. So this is just a collection of the many substructures that we're seeing in the near-infrared. The resolution is naturally good, so we can resolve these structures here. This is the effort by the Japanese consortium SEEDS with the Subaru Haichao. These are mostly via-sphere images that I'm involved in. So this is the DARTS program by Havenhaus 2018, and this is the follow-up by me and collaborators, and this is just a collection of the GTO, of the guaranteed time observation by Sphere. So I'm going fast here, just on an overview of the features that we have before really coming to shadow. Cavities. Cavities are the most obvious, probably, finding of these images here. Now we have very large cavities, that are tens of AU large, and there's certainly some material inside. We know that, the presence of near-infrared excess, accretion, as you tell me, and so on. But we certainly have these very, very large cavities of micron-sized dust grains. When we observe near-infrared light, we are certainly tracing the very small dust grains, micron-sized dust grains. Then we observe with ALMA, and we have the same cavities for large dust grains, or with gas, with some molecular species, and we can see that there are some differences in the size of these cavities here. So somehow the dust is not, and the gas are not behaving the same way. There are processes that can really differentiate the small dust grains and the large dust grains and the gas, and so on. So this is one of the elements that was historically considered to be due to planets. Forming planets there can really differentiate the dynamics of small dust grains, large dust grains, and so on. And then we have spirals, of course, grand design spirals. We're really catching our images here. We know they are relatively frequent. I'm putting a number, I'm not sure about this, but let's say it's less than 20% around Herbig stars. But at the moment, we have, from my point of view, at least this kind of spirals here, we have zero detection of spirals around T-Tauri star. So again, this is something to keep in mind. Their origin is highly debated. Planets, of course, are involved here, but I'm personally not sure about this. We have different opinions, and I don't think there's any ultimate answer at the moment. Then we have rings and other annular gaps, which are actually more frequent, around 30%. Any type of star, so T-Tauri, Herbig, there's not really any trend. Rings seems to be really ubiquitous. Young star, old stars, and so on. Again, planets seems to be the most, say, favored explanation for these disks. Still, I'm sure, from my point of view at least, whether the number of rings and the location of rings that we see is consistent with the planetary statistics that in the end we form. I'm not sure we really have this planet out here, or that planets are efficiently migrating inward to represent then the planetary, the final architects of planets that we see from Kepler and so on. And then we come to shadow. So shadows are these dark lanes here that have been seen probably the first time around 6 years ago or so, 6, 7 years ago, at least from these polarized images here. And they are in turn very diverse. Stefano already showed us something. No, they can be narrow like this, or very broad like here. They can be really pronounced. They can be really clear, like in this example here again, or there can be really a marginal fading of light, like you can barely see, like probably here. They can be constant in time, or they can be variable. So there's a really variety of shadows within this population too. And this is, I'm not sure you can really see, but this is probably the image that I made myself to convince me that these are real shadows. So I'm not sure you can see this. A sort of spiral here, probably from the beamer, it's not really clear, and then it's that in this moment that we have the sun coming. So, but then you can probably guess or squeeze your eyes that it's coming here again. So you can really see that this spiral here is disappearing here, it's going under the shadow, and then reappearing here again. So this is really clear that it's so unphysical to explain this unless you have a shadow. It's basically not providing you with light where the shadow, where the spiral is. We saw this already. Radiative transfer can explain relatively well and relatively easily the shadow of the shape of the shadow, as from this work by Sema Marina and collaborators, which are actually sitting in this room, at least they are in this conference. In this case here, this is the first example. We have very clear shadow here, and these are well reproduced by misaligned disk, very misaligned disk. I don't really remember the number here. It's probably around 40 degrees or 50 degrees. Actually, I don't remember. But the point is that these disk regions are not quite reachable by our images, and that's one of the few examples where we could see actually something. And that's by Henning-Avenhaus, and the shadow responsible for this very object here is actually imaged. And the funny thing is that here there's a companion, stellar companion, that we don't quite see in this kind of images, this type of images, because it's polarized light. But you can see that the morphology of this inner disk component here is not what you would expect here. It should be actually oriented like this, in principle, to cast shadows like this. So it's not really oriented like this. And then it's kind of strange that we have a companion here and still a lot of dust. So I'm not sure this is entirely clear what we're seeing here. We certainly have some biases and some artifacts, but there's certainly dust there that is scattering light. This is what I was mentioning before. So narrow shadows can be reproduced by very misaligned disk, like 72 degrees in this example here by Miriam Benisti in HT under 453. Whereas wider shadows are actually reproduced by smaller inclination, like in this example here, where actually half of the disk is very well illuminated, while the other half we have basically no flux detected except this inner region here, which is probably in turn responsible for casting the shadow, or at least this would be my interpretation. This we saw already from Stefano as well. When the shadow is larger than 180 degrees, we probably need two components. It's just impossible to create this shadow here with just one component, so we probably need an inner region inclined in a certain direction, oriented in a certain direction, and then another intermediate disk region, which maybe visible already in our images, I'm not sure, which is oriented in a different way. So the result is that once again we can learn something about the inner disk regions from the images. You may have noticed, or not, that when you have shadow, very often you have spirals. It's kind of an intriguing association between shadows and spirals. There is these three objects, but there's one more, the first that we saw, the famous one, HT142527. And I was intrigued by this paper here by Matthias Montesinos and collaborators, showing that in principle, because of the shadow, you can create spirals. That's a possible explanation. There is some criticism about this, but in principle, it's possible that because of the pressure gradients on the disk surface induced by the shadows, you may create this spiral, grand design spirals here. So in principle, you may not necessarily need planets to explain these spirals here, which is something that I personally like, as I told you. Finally, we saw that this shadow can be very variable in time, and this is an example here. You can see that there are two shadows, are always two, but their location is changing with time, clearly, right? You can see this. And also their width is changing. Like here is very narrow, is very, very narrow. Here seems to be a little bit broader. And the same happened for this example here by Thomas Stoker, this is by Paola Pinilla. You can see here there are actually two components. One very broad here, like this. And this super broad here, basically half of the disk. And the very narrow component, which is very localized here, dark lane, that you can see from the original images too.
Tell about the time scale. Nobody sees this.
Oh, yeah, sorry. So we're talking about, so these are different, we're not sure about the sampling, but this is 14 of August, this is 3 days later, 1 day later, 5 days later, and so on, but this is 5 years before. So this is 2012, 2015, 2016, and then on the same month, 13, 14, 17, 18, 22, and so on, of the same month. So I'm not sure about the sampling yet. We probably need a finer sampling, but this is certainly changing in less than, say, a few days, certainly. And the same here, this is from a few days, a few weeks at most. So these are objects here can be well considered as the face-on equivalent of our dippers and our UX Oriones with clear variability induced by the inner regions, and whether this inner variability is in turn due to companions or to variable magnetic fields is something that, of course, we cannot answer yet. Finally, just to mention that, but Simon's probably talking about this later today, so there may be counterparts in the millimeter for this shadow here, like in this example here, where we have, again, the near-infrared scattered light, and this is ALMA. You can clearly see that along the azimuthal location of the shadow, there's also a dim in the millimeter. But Simon will tell you about this later today. So about demography, now we have quite a large number of shadows, so we can really start to see how these shadows are distributed across stellar mass, disk mass, and so on. And now I'm showing you two plots that are representative for me. And here you will see the time, so the age of the star, and here you will see the stellar mass. Simon, I just showed you your image. So to say 10 seconds before you will have seen your images. Hi, Simon. And this is the result. So this is the distribution in time and stellar mass of all the objects that we have observed, or most of the objects that we have observed in scattered light, near-infrared scattered light. It's intriguing to see, before coming to shadows, that we have this complete desert, this perfect desert here, which, in my opinion, is due to the fact that these stars are still embedded. If they're massive enough, they still preserve this envelope, and so it's just not visible in the visible. And then we can clearly see also that the time in which an Herbig is actually an Herbig is very short. This is logarithmic, so you may consider this is slightly larger in natural scaling. But you can clearly see that when a star is 2 solar mass, then just for a short time would be a Herbig star, but for a long time would be an intermediate mass Centauri star, which is actually not very well imaged yet. This region here is actually due to the adaptive optics. These stars here are very faint, and so we cannot really observe them. So we don't know anything in near-infrared about old subsolar star mass stars. And this is the presence of shadows. So I was probably naively considering that the shadows are typically old, let's say around old objects. This is certainly true for some of these. In a sense, they are as old as the disk can be, because we have no disk basically after this regime here. However, you may also say, well, you know, it's actually that you don't know anything about these stars here. So probably what you see here is not that they are old, but just that they are typically found around super solar mass stars. There's just one example. From my point of view, it's Gigi Tau, but this is a multiple system. It's actually a quadruple system, I don't remember. So we certainly have interaction among stars within the cavity. So this particular object is a very special one. Other than that, all these objects here, there's no shadow. So shadow seems to be found around the relatively massive stars, relatively massive in a sense in our sample. Same for near-infrared excess and far-infrared excess calculated from the ACD. So this is telling you something unresolved about the disk. This is where a full disk will sit. So this is basically 15% of near-infrared excess, and the far-infrared excess is low because the outer disk is not really illuminated. All these are transition disks, those with a large cavity. They can allow you to have a lot of far-infrared excess and not so much near-infrared excess because the inner regions are depleted. These objects here are probably those where we have some extra material that is contributing to both excesses here. The near-infrared excess very inside, close to the star, and the far-infrared excess somehow uplifted, like an envelope. And this is the location of shadows. This is more clear, probably. Shadows are associated with a high near-infrared excess, almost in any case. Except one exception, you know there must be an exception, right? But except this, we always have shadows associated with high near-infrared excess. Even more interestingly, now I'm plotting near-infrared disk cavity. So it's red when you see a near-infrared disk cavity from imaging. And you can clearly see that among the high near-infrared excess, so just split this into two and look at this sample here, when you have a disk cavity, you have a shadow, always. So if you have a high near-infrared excess, or you have something hot and reprocessing material inside, then you always have a shadow when you have a cavity. So somehow these two things are going together. Does it mean that when you have uplifted material close to the star, this is also misaligned in order to provide a shadow? This is probably a naive view, but this is what I would see at the moment. So I'm going to conclude with two additional topics, just to remind ourselves that we have other indirect proxies of the inner disk. And one is the fact that we can begin to characterize even the central unresolved polarization from the disk, because you may consider that we have a resolution, yes, that is true, and anything that is polarized in the stellar beam will also appear in our images, it just will be unresolved, because it will be considered like the star is polarized. But it's not necessarily a star, it can be the inner disk, of course. It just has to be smaller than, say, 5 AU, if our resolution is 5 AU or 8 AU. And this will be smeared with the PSF, and so it will appear also larger regions. In other words, what we see here is a non-resolved component of the polarization from this disk. So we have the disk here, but we also have a polarized component at less than 5 AU. And you can see the orientation is basically around the bright lobes that we have here. This is telling you that the orientation of the inner disk at 5 AU is roughly the same as the outer disk, which is an important information, I guess, right? We don't have big disk warps in this example here. This is the famous guy I've probably seen with two protoplanets, like PDS-70 from Kepler et al. And Müller et al. And so on. And so I was just plotting this for a number of objects from the DART survey that I told you about. And you can see that in many cases, actually, the angle between the outer disk that we have from ALMA and so on, and the inner disk that we can actually constrain from this centrally unresolved polarization is very small. 11, 7 degrees, 8, 7, 3, 5, 3. There are examples where this is very large. In some of these cases, actually, this is due to interstellar polarization. We should correct for it, but this is certainly not true. But there are also examples like this, where the extinction is low, so this is probably actually a real effect. So this is probably telling you that the inner disk at 5 AU is 30 degrees misaligned with respect to the outer disk. So disk warps and all the rest of the story, as you know. To conclude, our white tower appears many times in this conference, so I thought to just show a few slides about this. We have a paper accepted, it's out this year on the sphere images of this object here, where it's mostly dedicated to jets. We heard about jets not so much in this conference, especially for RW Riga. This is the jet of RY tau detected with sphere. So H alpha, iron 2, and so on. The important thing is that the ALMA disk that will sit actually oriented like this, it's not seen in the near infrared. So the near infrared is completely dominated by the envelope, by this large cloud here. We saw something similar yesterday from Boris's talk. And you can see also that the disk is sort of wiggling. There are substructures like this one here, and then there's another one outside. I'll show you, like here, this one here, and then basically nothing here. And since we have different epochs, we can calculate the velocity of these substructures here. And it's interesting that the ejection time of this structure here will correspond actually to the maxima of the photospheric curve of the star. We know this source here is certainly due to occultation, but there might be also a component for the accretion, let's say, when the maxima are actually, let's say, on a scale of a decade, it's actually due to accretion increase that actually have, say, an imprint on the jet, on the emission of the jet. The final thing is that the jet seems to be wiggling, and this is best explained with the presence of a disk warp, so the processing disk warp. So we may have a disk which is actually misaligned, and this is processing with respect to the outer disk and the effect that the jet is doing like this on a time scale of, say, a few months or years. And the effect of this is that the jet is doing something like this. I'm concluding, the near-infrared direct imaging cannot really characterize the inner disk yet, but we are getting there. So thank you very much.
So questions, please.
Yeah, I have a general question now. Now that you know about all the near-infrared images of protoplanetary disk, I wonder if there is any work that tried to relate the way that we classically define transitional disks, which was based on the spectral energy distribution, with the images. I mean, all the transitional disks from the SEV perspective correspond to disks that show holes and the other way around, or?
Yes and no, in the sense that the ALMA images, I think they, well, I can maybe know more better. The ALMA images, most of the time, or even always, they show the cavity that you infer from the ACD. Whereas, from the near-infrared, this is not always true. There are many cases where you would say there's a cavity. There is certainly a cavity. You can see from the ACD. But in near-infrared, you don't see it. This can either mean that the cavity is smaller than our inner working angle, as I showed in the first sample, in the first slide, so maybe 10 AU, 5 AU or so, or that the cavity is only for larger grains, and not for the gas, and not for the micron-sized grain. So that's a possible explanation for the discrepancy.
The other way around?
There are cases where you see nothing from the ACD, and then with ALMA you see a clear cavity.
This. The ACD of this example here, I think it's a continuous disk, but from ALMA you actually see a small cavity. Yeah, yeah, that's true.
You mentioned that about 10% of Herbic stars.
Sorry, I gotta give you the mic.
You mentioned that about 10% of the Herbig's disks have spiral structure, right? And then you said that T-Tauri stars don't have that. Does it? Do you mean the scattered light, or because I know Elias 227, this is a T-Tauri star, if I'm correct.
Good point, sorry, good point. Thanks for raising this. So there are different type of spirals from my point of view. Not sure I actually said that. No, I didn't put it. So this is a scatter light we see in the near infrared. Recently, also in the millimeter, spiral arms have been seen. But this is never in the same object as this. So when we have spirals in the near infrared, these are not seen in ALMA continuum. On the other hand, when you have the spirals in the millimeter, like Elias 24 or a few other examples, you don't see it in scatter light. Also, as I showed you, no, I didn't show you actually, but the spirals are typically old, so in this plot here, they will sit always here, sometimes somehow associated to shadow, whereas Elias 24 and all the other objects with spirals in the millimeter are actually sitting here. Completely different. There's a clear dichotomy between the spirals that we have in the millimeter and those that we have in near infrared. So that's a clear indication that those spirals are due to different processes. Maybe when they are young, there's still gravitational instability, and when they are old, planets or shadows, but they're clearly different processes. But you're right. Thanks for raising it.
When we had the first time idea of disks around young stars, we thought about disks as sort of homogeneous things, and then we realized that they are not necessarily disks because we see. Inner disks we don't really know. And what disturbs me is that when you need these very big shadows, you have to tilt the inner disk, but then you have to tilt the ring. It starts to be a little bit complicated. Has there ever been any work on that the inner disk has some structure, that it's not like a disk, but it's something else?
I'm not sure, probably not the right person to ask. I'm really not doing any near infrared interferometry, but at least from the near infrared interferometry images that I see, the orientation is the same as the outer disk most of the time, at least from Bernard Lazarev's work and so on. Sorry. I'm not sure about the presence of structure inside. We cannot say so much. In particular, we are still biased toward larger disks. So we don't even know whether smaller disks have substructures. Because smaller disks, say of 10 AU, we don't see them. In other words, we don't know whether a small disks are actually a truncated version of the larger disk or they're a scaled down version of the large disks. So the truth is that I cannot answer your question. I don't know if anybody can do it.
Not enough resolution.
Not yet.
Yeah. More questions?
We know that sizable part of T-Tauri stars demonstrate A tau variability. These stars are observed near to the H-on. But if such star is observed pole-on, you will observe the moving shadow. And such object has to be widespread among T-Tauri stars.
Can you remind me the stellar mass of a tau? Do you know? Is it an intermediate mass T-Tauri star or a low mass T-Tauri star? Low mass T-Tauri star.
Yes.
Okay.
Classical T-Tauri star.
Classical T-Tauri star. Okay. Yeah. So it would actually sit, say, in this plot here, would actually sit somewhere here. Okay. Good to know.
Okay. The last question.
I was intrigued by your plot. I was really intrigued by your plot of the polarization orientation of the unresolved component, because it seems that in most cases you really have no misalignment. How do you make those shades then?
Good question. One possibility is that unfortunately this data is still chronographic. So what you see here is actually a misalignment between, let's say, 10 AU and 100 AU. It's not from 1 AU to 100 AU. So this is just telling you that there is no major disk warps between 100 and 10. It's still possible that maybe the disk is broken between 10 and 1, and then the misalignment occurs on a scale of 1. Unfortunately, with disk imaging, we cannot access the 1 AU yet. We do ALT maybe in a few years.
Okay, thank you very much.
Thank you.